Okay, today we're looking at 4.3 equivalent fractions. This is something you're very familiar with. As all these sections in Chapter 4, you've probably seen a little bit of these, but we just add um, um, just a little bit of algebra with some of the basic math that we've learned. And equivalent fractions is one of those things that you've seen and done. We're going to add some algebra, meaning we're going to throw some variables into the fraction, and we're going to simplify them. Not hard, just something you haven't seen. So there's a couple things we need to know. Two fractions that represent the same number called equivalent fractions. Okay, a fraction can be written in any form. You're used to reducing fractions, but certainly fractions may not be reduced. Um, and there are several. You can think of a number or an infinite amount of fractions that will equal each other. And we're going to look at that here in a second. To write equivalent fractions, multiply and divide the numerator and denominator by the same non-zero number. So what I want to do basically is just to do the same thing on top as I do on bottom, or do the same thing on bottom as I do on top when I'm making equivalent fractions. So the instructions are to write two fractions that are equivalent to the given fraction. So if I want to do that, I need to either multiply the top and the bottom by the same number or divide the top and the bottom by the same number. In this case, let's divide. If we divide by 5, I had to do that to the same thing to the top and bottom. Sorry, and then I did a 10 there. 5 divided by 5 is 1, 10 divided by 5 is 2. 1/2 is equivalent to 5/10. They equal the same number. Okay, another way of doing this would be to multiply. What if I multiply the top by 2 and the bottom by 2? Well, that would give us 10 over 20. These two are equivalent, and they're both equivalent to 5/10. I can also multiply the top and the bottom by a different number. Let's say 10, and get something that looks like this. All of these fractions are equivalent because they equal the same number. 6/9. Well, I can divide here. I don't have to divide if I'm doing this little section in the book. I can always multiply, but I'm doing both here. If I divide the top and the bottom by 3, I get an equivalent fraction, which is 2/3. Let's say I multiply the top and the bottom by 2, I'm going to get 12 over 18. Okay, all of these fractions are equivalent. Here, we can actually divide the top and the bottom by 2, and I get 6 over 10. I can keep going. I can divide the top and the bottom by 4, and I can get 3 over 5. All of these fractions are equivalent to each other. Okay, 18 over 24. Let's not divide, let's multiply. I can multiply the top and the bottom by 2. I get 36 over 48. I can multiply the top and the bottom by 10. I can get 180 over 240. All these three fractions are all equivalent because they equal the same thing. Okay, write the fraction in simplest form. Now, this is what you're used to doing. You see a fraction that needs to be reduced, and you automatically think, I've got to reduce it. So what we have to do is find the GCF of 4 and 14, and in that case, it is 2. And if I divide the top by the GCF and the bottom by the GCF, I'm going to get 2 over 7. And this is in simplest form because 2 and 7, their GCF is 1. 2 and 7 are relatively prime. So a fraction is in simplest form when the numerator and the denominator are relatively prime. Here, what number goes into both 8 and 36? Well, I think that's 4. So if we divide the top and the bottom by 4, we get 2. Maybe over 9. So 2 ninths. This is our answer here. Here, what goes into 2742? Well, I know 3 does. Here we get 9 over 14. 9/14. 9 and 14 are relatively prime, so that is in simplest form. 28 and 49, well, 7 goes into both of those. So I get 4 over 7. Okay, and that's simply writing fractions in simplest form, and you've done that before. This is what we've added today. We're going to throw some variables in these fractions, and we're going to reduce the fractions that have variables, or we're going to simplify them. So what we're going to do with each of these is expand the variables. We want to write it without exponents. So the top stays the same here. But the bottom, I want to write this without exponents. Okay, then I'm going to reduce the numbers. Well, 10 and 15, if I divide the top and the bottom by 5, I'm going to get 2 over 3, right? And then what I do is I cross for every variable I have on top. If I've got one on the bottom, I cross it out. So I'll cross out pairs because y divided by y is equal to 1, right? It just becomes 1. So what do I have left? Well, I've already reduced this. I got 2/3. I have an x on top and a y on bottom, and I'm finished. And I just write that in. Y over y became 1, but I don't have to write the 1, obviously. Look at this one. All right, 27xyz and 3x. Well, I don't have any exponents, so I don't have to rewrite this. I'm going to reduce the fraction. 27 over 3 is 9. Okay, then I've got 1x here and 1x here. That becomes 1. What do I have left? Well, yz on the top in the numerator. Actually, in the denominator, this doesn't go away. It just becomes 1, but we never write a 1 in the numerator. Okay, never need to do that. Okay, here, let's go ahead and write it without exponents. 22x y over 24x y. Okay, I want to reduce the fraction. If I divide by 2, I get 11 over 12. Okay, then let's just cross out pairs here. Y over y is 1, y over y is 1, and again, it doesn't have to be right under. It doesn't matter. If I got a y on top and a y on bottom, I can cross it out. I've got an x and an x here. What do I have left on top? Well, I've got this x, and on bottom, I've got this y. So I put an x on top, y on bottom, and I'm finished. Here, now the 35 over 35, well, that reduces, doesn't it? Becomes 1. Okay, but I need to write out these variables, xx, and then xxx. Well, this crosses out, this crosses out. What do I have left? Well, I have an x on bottom. But what's left on top? A 1. Okay, it's not that everything just disappears, it just becomes 1, because anytime you divide a number by itself, it's 1. So I've got a 1 on top, and I have an x on bottom. Okay, if the x is on bottom here, it's got to stay on bottom of my answer. I can't, and a common mistake is going, well, I've got nothing up here, I'm just going to write my answer as x. Well, no, x is in the denominator. I can't just all of a sudden stick it in the numerator. That would be wrong. Let's do a word problem and we'll be finished. Suppose that the water level of a river is 34 feet and that it is receding at a rate of 0.5 feet per day. Well, that is definitely a rate, and rates always tell you what they're multiplied by. It's the second unit right here, days. Write an equation for the water level L after D days. Well, we already said 0.5 is multiplied by days, so that's 0.5 D. Okay. Now, if it starts at 34 feet and it's receding, that means it's getting lower. So we're not adding. We're used to adding this. But this one's actually receding by this rate. So if I start at 34 feet, I can't add this. It's actually receding, so I'm going to have to subtract it. And that's going to equal the water level, okay, after D days. Well, it says, in how many days will the water level be 26 feet? Well, if I just substitute 26 for L, because that's the water level, okay, I can actually solve this by subtracting 34, and I get negative 0.5 D is equal to negative 8. Divide by both sides by negative 0.5 D. D is equal to positive 16. So in 16 days. Okay, this again, basic linear word problem. We had a rate. The total is here. It was not really given to us until here. This was actually the total, but they gave us a variable to put in place of the total. So in this case, we had two variables when we wrote this equation, but then they gave us a total to substitute for that so we could solve. And that is it for today.